This is grade 12 University Physics, Unit 5 Modern Physics, Lesson 10 Quantum Information. Specifically, we're going to try a challenge and look at a simple quantum algorithm. But first, to do that, we need to quickly review the Mach-Zehnder interferometer. So in the Mach-Zehnder interferometer, we have first a laser that will fire light towards a beam splitter, which will then split the beam into two directions. Each one will hit a mirror, bouncing back to another beam splitter, which again leads into two directions that can be detected at either detector 1 or detector 2. Let's take a single photon. Now if this photon were to go through, you can probably see it has 4 different options. One option, it goes to detector 1. Another option to detector 2. And our third option to detector 1, and our fourth to detector 2. So we have 4 options, 2 of which go to detector 1, 2 of which go to detector 2. So you would guess there's a 50-50 probability of this photon being detected in 1 or 2. However, if we're not actually observing the photon, it's going to act more like it's in a state of superposition, or more like a wave. So if we were to draw a wave throughout this interferometer, we can see that we get constructive interference at one detector and destructive interference at another. This means that there's a 100% chance of seeing the photon where we have constructive interference, and a 0% chance where we have destructive interference. Now let's look at the problem. Luna has a function f of x that takes as input a single bit valued at 0 or 1 and outputs a single bit, 0 or 1. Luna refuses to tell you what f of x is, but she's willing to let you query it. You can give Luna any input of bit x, and she'll give you back the corresponding output bit f of x. Your task is to determine whether the function f of x is constant, such as 0, 0 or 1, 1, or not, such as 1, 0 or 0, 1. So we have 4 possible functions here. If the bit x is 0, the function could be 0 or 1. Similarly, if the bit x is 1, the function could be 0 or 1, which leads to these following 4 options. Now, if this were a classical computer, you would have to ask 2 questions. Those being, what's f of x if x is 0? And what's f of x if x is 1? But let's see if a quantum computer would be able to do any better by looking at a simple quantum algorithm. Going back to the Mach-Zehnder interferometer, Luna is going to place a wave plate which will shift the phase of the wave by 180 degrees if f of 0 is 1 at the top half, and if f of 1 is 1 at the bottom half. So here you can see that if the value of f of x is always 0, whether x is 0 or 1, no wave plate is placed anywhere, and we get 100% detection at one detector. But if we have a wave plate placed in the upper zone, then we get a 180-degree shift, and now if we follow this wave through, the location where we have constructive interference and destructive interference have switched, and we now detect the light at the other detector. This would happen if we had covered the bottom half of the interferometer with a wave plate instead of the top one as well. However, if we were to cover both of them, then again, the areas of constructive and destructive interference now switch back. So you can see that if we look at the functions, If f of x is constant, it will always be detected at our top detector here. Whereas if it's not constant, it's always detected at the bottom. So for a quantum computer, you only need to ask one question. Where is the photon detected?